Hello students. Yesterday we discussed about cell potential and electrode potential. We saw its examples, that is its derivation or how to find out the concerned cell potential or the electrode potential. Now today we are going to actually solve some problems that is again taken from your textbook for your convenience. So the first one, calculate the voltage of the cell, and they are given the cell, that is Sn, single vertical line, then Sn2 plus. They are given the concentration as 0.02 molar. Double vertical line, we know that double vertical line means they used a salt bridge. Then Ag plus, again its concentration is 0.01 molar. Again single vertical line, Ag at 25°C. Keep in mind this cell worked at 25°C, and they are given the standard value of E0 of Sn, that is minus 0.136 volt, and that of Ag, that is E0 of Ag is 0.800 volt. So see the solution, how to solve this problem or how to find out the cell voltage. So first we write the cell reactions as Sn gives Sn2 plus plus 2 electrons, that means loss of electron takes place, that's why it is oxidation. Then Ag plus 1 electron, and that gives Ag only. So if we observe its oxidation state, that is Sn having 2 plus and that of Ag having 1 plus. So to balance this one, we have to multiply the second equation, that is the reduction at cathode, by 2. The overall equation is multiplied by 2. We know that in the mathematics, if we multiply any equation with the same value, then its total value remains as it is. So we will multiply that whole equation by 2. That is just for our convenience. Then the net cell reaction becomes Sn plus twice of Ag, Sn, yes, plus twice of Ag plus, that gives Sn2 plus twice of Ag. Overall net cell reaction is this one. The cell potential is given by, now in the next slide, E of cell is equal to E0 of cell minus 0.0592 volt. Now why we are just directly considering 0.0592 volt? Because the cell is worked at 25°C. That's why we are considering that value directly. Divided by 2 means 2 electrons participate in the cell reaction. See in the previous slide, that is 2. See in the net cell reaction, they are given 2 electrons. Yes, in the oxidation anode, that is plus 2 electrons they are given, and again in the reduction at cathode we are multiplied that overall equation by 2. That means electron again becomes 2. That's why we are considering that 2. So I'll repeat once again, E of cell is equal to E0 of cell minus 0.0592 divided by 2 log to the base 10, then concentration of Sn2 plus divided by concentration of Ag plus. Okay, so we just substitute the value of that concerned species, that is E0 of cell is equal to E0 of Ag minus E0 of Sn is equal to 0.8 volt plus 0.136 volt. Just solve this sum, we get the answer 0.936 volt. Hence E0 of cell is equal to 0.936 volt. That means initially we just find out the value of E0 of cell, then the next one is the, we know that is the Nernst equation, that is E of cell is equal to E0 of cell, E0 of cell minus 0.0592 divided by n log to the base 10, then the concentration of concerned species. That means in this problem Initially we find out the value of E0 of cell, that is E0 at standard condition, then the given condition. So hence E of cell is equal to 0.936 volt minus 0.0592 divided by 2 log to the base 10, 0.02 divided by 0.01 raised to 2. If we solve this equation, we get 0.936 volt minus 0.0592 volt divided by 2 log to the base 10, and if we solve that term, that is 0.02 divided by 0.01 raised to 2, we get its answer as 200. That's why log to the base 10, 200. When we solve that equation, we get the next line, 0.936 volt minus 0.0592 divided by 2 into log to the base 10, 200 is 2.303. So 0.936 volt minus 0.0681, and if we solve this one, we get the answer 0.8679 volt. That means the overall E of cell or the voltage of cell is 0.8679 volt. In this way we can find out the cell voltage or the cell potential. Now in the next problem, it is regarding the electrode potential. So in the next problem, the standard potential of the electrode, they are given the electrode Zn2 plus in bracket 0.02 molar, then Zn, single vertical line is there, and then Zn. That means Zn acts as a electrode and it is dipped in its own ionic solution, is minus 0.76 volt. Calculate its potential. So they are given a problem, that is a reduction. They are given the reduction electrode, that is Zn is in the vicinity of Zn2 plus. That means Zn is dipped in its own ionic solution, and this is calculates its potential, and they are given a standard value, that is minus 0.76 volt. Now as a previous lecture, we can calculate its electrode potential also. Now first of all, we have to see its reactions. Zn2 plus 2 electrons, so that accepts 2 electrons and forms a Zn as a neutral. Then by applying Nernst equation to this reaction, we get E of Zn is equal to E0 of Zn minus 0.0592 divided by n log to the base 10, 1 divided by concentration of Zn plus 2. So if we substitute the value, that is they are given in the problem, E0 of Zn, that is minus 0.76 volt plus 0.0592 divided by 2, that is n having value of 2, because there are 2 electron participate in this reaction, that's why it is 2, log to the base 10, and its value is 0.02. If we solve this, we get minus 76 volt plus 0.0592 divided by 2 into minus 1.6990. If we solve further, we get the final answer minus 0.81 volt. So this is the final answer of this problem, that is the potential, electrode potential of this concerned electrode is minus 0.81 volt. So this is a very simple one. Now the next one, that is reference electrode, that is standard hydrogen electrode. Okay, in the previous lecture we saw that standard cell potential and equilibrium constant. So this one is reference electrode, that is a standard hydrogen electrode. Now see that as shown in the diagram, there is a vessel, some glass vessel is there, and there is one inverted tube is there, that is again in the center of that there is a small cylindrical tube is there, a single wire, that is copper wire is there, and at the center of that there is a mercury below that, that wire goes through the mercury, platinum wire is connected to that, and finally platinize platinum plate. In this way there is an arrangement. Or in the other way, we go from center to outward, there is a small square is there at the center, that is a platinized platinum plate. Now that platinized platinum plate is connected with platinum wire at the upper side of that. Again, above that there is a mercury. Again, above that there is a copper wire that is removed completely outside. Now that mercury is in the glass tube is there. Again, there is a bigger glass tube, that is like inverted jar like a glass jacket, that is known as a glass jacket. And finally there is one vessel is there, a glass vessel is there. So in this way there is an arrangement of this standard hydrogen electrode. And for the glass jacket, there is a one inlet is there at the upper side, and at the lower side, that is in the vessel, there are small holes to pass out the hydrogen gas. So from the topper side, we can say that there is a dry hydrogen having a pressure of 1 atmosphere is allowed to pass inside. Then that gas is absorbed on the plate of platinized platinum plate, and that vessel contains a solution having H plus ions whose concentration should be 1 molar. It is a standard hydrogen electrode, that's why its concentration must be 1 molar. So platinized platinum plate is there, and that is dipped in the H plus ions solution whose concentration is 1 molar. Now we are allowed to pass the pure and dry hydrogen gas in the glass jacket from the upper side, and that gas, some of the molecules get adsorbed on platinized platinum plate, and the other one is removed out from the lower side of the glass jacket. And this process takes place continuously, that means until this electrode works. So this is the basic arrangement of reference electrode, that is the standard hydrogen electrode. In examination, they may directly ask you draw the diagram of SHE. So you must know what is meant by SHE, that is a standard hydrogen electrode. So this is the arrangement of standard hydrogen electrode. We'll see in the next slide. Formulation, how to formulate this electrode, that means one mathematical type of writing is there which gives the whole information regarding to that electrode. So H plus in bracket 1 molar, that is its concentration of that H plus ions, that may be sulfuric acid or HCl. Then single vertical line is there, and that is H2. H2 is a gas whose atmosphere pressure is 1 atmosphere, and again single vertical line, and that is a PT, that is a platinum. Now it is very important we understand that there is a platinum wire is used only for the electrical contact, and it do not acts as a electrode material. So here is a electrode material is a hydrogen gas, but that is in a gaseous state, so it is very difficult to handle it. That's why we are using a platinum wire. So that's why they are written a platinum wire. So again we can read this electrode as PT single vertical line, then H2 in the gaseous state having a pressure of 1 atmosphere, again single vertical line, and H plus ions in bracket 1 molar. That means any H plus ion solution whose concentration is 1 molar. So this is the formulation, or we can say representation of the electrode. Now the electrode reaction. Now how the reaction takes place on this electrode. One more thing is there, though it is a standard hydrogen electrode, it may act as a cathode or anode in a cell, because in every cell we know that there are 2 electrodes. So this is the only one electrode. So either it acts as a hydro oxidation electrode or the reduction electrode, that depends on the other electrode material which we are using in the cell. So it is not necessary if here it is given that is a reduction electrode, so it doesn't mean that the always reduction reaction takes place on the hydrogen electrode. So it depends on the other electrode material which is used with this cell. So the electrode reaction, in this case it acts as a reduction one. So twice of H plus 2 electron, that gives H2, and its E0 is considered now is equal to 0.0 volt. It is very important. We are considering its value as 0.0 volt at 25 degrees Celsius and 1 atmospheric pressure. So it is a gas material, that's why we have to consider its pressure. So it is a 1 atmospheric pressure should be there, and its temperature should be 25 degree Celsius at that situation, and its concentration should be 1 molar. At that situation we are considering, it is very important, we are considering its standard value, that is E0 is equal to 0.0 volt. By using this value we are calculating the electrode potential of other material. So we are considering it 0.0 volt. So that's why it is known as primary reference. By using this one we can find out the values of other electrodes potential. So that's why it is known as primary electrode, primary reference electrode. Now what are the applications of SHE? Applications of SHE. So SHE is used as a primary reference electrode, just now I told you, to determine the standard potentials of other electrodes. This is the main thing. Now what are the difficulties? Difficulties in setting SHE. Now the first one, it is difficult to obtain pure and dry hydrogen gas. It is very difficult to obtain a pure and the dry hydrogen gas which we insert from the outer jacket or the outer jacket's inlet. And the second one, the pressure of hydrogen gas cannot be maintained exactly at 1 atmosphere throughout the measurement. So it is very again difficult to maintain its pressure of 1 atmosphere. And we know that there is one condition for the standard state. For the standard one, there should be a 1 atmospheric pressure and 1 molar concentration should be there, 25 degrees Celsius temperature must be there. So it is very difficult to maintain the pressure of 1 atmosphere throughout the measurement. So these are the main difficulties in that. Then the third one, the concentration of H plus ions should not be exactly maintained at 1 atmosphere. Now why it is not maintaining 1 atmosphere? Due to bubbling of the gas into the solution, evaporation of water may takes place. This results in changing the concentration of the solution. So this is the main reason why it is very difficult to maintain its concentration as 1 molar. Now in the next diagram, that is a cell is given, that is a determination of standard potential using SHE. That means whatever diagram just now we saw, that is, I'll show once again, reference electrode, that is a standard hydrogen electrode. It is one of the electrode, we use this electrode in a cell. So now this is the complete cell diagram, determination of the standard potential using SHE. Okay, in this diagram what we can observe, the SHE is connected with the zinc electrode and zinc is dipped in its own ionic solution, that is zinc sulfate. In this way we can use SHE to calculate the electrode potential of other one. Say they are saying in the application SHE is used as a primary reference electrode to determine the standard potential of other electrode. So in this 5.7 diagram we can see that SHE is connected with the zinc electrode and zinc is dipped in zinc sulfate solution. That means we know that SHE having a voltage of 0.0 volt, E0 of hydrogen gas is 0.0 volt. So whatever cell potential we will get, that will be the electrode potential of Zn in this particular case. Okay, I'll explain again once again. I'll just repeat once again. Please listen carefully. We know that the E0 value of SHE is 0.0 volt, and in this case, in particular diagram, that is 5.7, we are connecting that SHE with Zn. Zn dipped in zinc sulfate solution. That means when we apply this one and we calculate the cell potential by applying the Nernst equation, whatever value we get, that will be the electrode potential of Zn. In this way we can find out a electrode potential of other elements by using standard hydrogen electrode. Now the next one, galvanic cells useful in day-to-day life. So in the galvanic cells in day-to-day life, so it is a secondary voltaic cell, dry cell. Again it is known as dry cell. It is a cell without a liquid component, but the electrolyte is not completely dry. It is a viscous aqueous paste. So though we call it as a dry cell, but it is not completely dry. They said it is a viscous aqueous paste. So in the construction, generally I'll just give you one more information. This cell we generally use in our household clocks, which we use in our houses. A big clock is there, in that we use this one, dry cell. As well as in the older time it was used in the batteries or torch. This is known as batteries, but it is used in the torch also. So it is known as a dry cell. So how it is constructed now? See, in the bottom of Zn container there is a container. We will go from outside to in. So at the outermost side there is a Zn container is there. Then beneath to that is paste of NH4Cl plus ZnCl2, and at the center there is a graphite rod is there given. Then in the vicinity of graphite rod there is a paste of MnO2 plus carbon. Then the outermost side is a Zn container. Then Zn container and the paste is separated by paper spacer is there, and at the top they are using a brass cap. So this is the construction or the description of the diagram. Now the next one is cell reactions. So cell reaction, that is oxidation at anode. So in the oxidation, we know that oxidation means a loss of electrons. So Zn gives Zn2 plus 2 electrons, and in the reduction we get twice of NH4 plus 2 electrons, that gives twice of NH3 plus H2 gas. Then that H2 plus twice of MnO2, that gives MnO2 O3 plus H2. So the net reduction reaction at cathode is given the combination of these two reactions, means which one, that is twice of NH4 plus 2 electrons plus twice of NH3 plus H2 plus H2 plus twice of MnO2, which gives MnO2 O3 plus H2. So we will combine this reaction and we will get the net reduction reaction at cathode, that is twice of NH4 plus 2 MnO2 plus 2 electrons, which gives Mn2 O3 plus twice of NH3 plus H2. So this is the reduction reaction at cathode. Now the net cell reaction is Zn plus twice of NH4 plus twice of MnO2, which gives Zn2 plus Mn2O3 plus twice of NH3 plus H2. The ammonia produced combines with the Zn2 plus to form a soluble compound containing complex ion. This is okay. What they are saying, ammonia produced combines with the Zn2 plus. See in the net cell reaction at the right hand side of the arrow, that is a twice of NH3, that ammonia combines with Zn2 plus. Okay, that combines with Zn2 plus of product side of the net cell reaction, that is Zn2 plus Mn2O3 plus twice of NH3. That means that twice of NH3 combines with the product side of Zn2 plus. That combines and that forms a complex ion, that is in the square bracket Zn, then in the small bracket NH3 bracket complete, again there is a 4 is written, then Again square bracket is complete and twice of H plus. So this is the net cell reaction and the complex is formed as the reactions are proceed. The next to that is use of a dry cell. We'll see in the next lecture. Thank you.